the packet? Azam, do you have it? Which one? The packet. We're on 10.6. Alex, do you have yours? Maria, you have yours?
Yep.
And Claudia? Okay, here we go. So last time we wrapped up looking at solving quadratic equations using any of the three methods, completing the squared quadratic formula, or normal factoring. So now we're moving on to looking at these graphs and how do we graph them in a quick and convenient way. Now, I could be wrong, but I feel like we might have done this before, so you'll have to correct me if I'm wrong. What I'd like us to do first is write down the general formula for graphing a quadratic. So everyone with me, go ahead off to the right-hand side of your page here. What I'd like you to write down is f of x equals a x minus h squared plus k. Now, at first glance, that might look a little complicated. Like, what are all those terms? Well, that is the transformed equation of a parabola. So if we were to just write down the equation of a parabola, it would just be f of x equals x squared. And let's see. None of the graphs that they've given you are the graph of a parabola, but the property of a standard parabola graph, x squared, I'm just going to draw it on top of one of these, would be that you start at 0, 0, and in fact, no, which one should we do? Everybody come down to graph part D. You come down to graph part D. Let's graph a standard parabola. I want you to get the feel for it. Answer D is not correct, so we can just graph right over it. If you want to graph a standard parabola, you notice that you have the vertex at the bottom of the parabola, and then you go up and to the right and up and to the left, right? Well, how do you go up and to the right and up and to the left? It's not a straight line. It's a curve of some sort. Well, what is the curve? The curve actually follows a very simple pattern called 1, 3, 5, etc. What are the numbers 1, 3, 5?
The y.
Hmm?
The y value.
Oh, those are going to be the y values, but literally the numbers 1, 3, 5, 7, 9, 11.
Odds.
They're odd numbers, so we're just counting by odds. So here's how it goes. If you want to graph a standard parabola, you're always going to go right 1, and then you go up 1. Right 1, up 3, right 1, up 5. So that's how we're going to go. We're going to start at the vertex and go right 1, up 1, and then right 1, up 3, 1, 2, 3, and then right 1, up 5, 1, 2, 3, 4, 5. And then right 1 up 7, 1, 2, 3, 4, 5, 6, 7. And if you keep going with that pattern, that's what a parabola does. A parabola will go, instead of a constant slope, you know how if you would do the line y equals mx plus b, and let's say that you got a constant slope of up 3, right 1. You would just always be going, up 3, right 1, up 3, right 1, up 3, right 1. But in the case of a parabola, it's not constant. The vertical increase changes and becomes more every single time. So it's right 1, up 1, right 1, up 3, right 1, up 4, right 1, up 7. If you want to graph the left-hand side of the parabola, you do the same thing. You go left 1, up 1, left 1, up 3, left 1, up 1, 2, 3, 4, 5, and left 1, up 7. And that gives you your characteristic shape of a parabola. That's just the characteristic shape. But folks, it's very important, as we graph parabolas today, it's very important that you show dots, right? Don't just go in there and graph a U shape. That's not what we're doing. It's very important that you draw the dots, and the dots are according to the pattern of 1, 3, 5, 7. Maria, did you have a question? Oh, okay. Any questions on that part? Why do you suppose it goes according to the numbers 1, 3, 5, 7? Why is it going by odd numbers? For instance, this is the function y equals x squared. What if I did a table of values right now? And I'm going to put in 0, 1, 2, 3, and 4. So that means I'm going to go x values 0, 1, 2, 3, and 4, just like I just did. What if I plug in 0? What do I get? 0 and 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. And 4 squared is 16. Well, what are the differences? How much are you going up by every time? Yeah, you go by 1, and then 1 to 4 you go by 3, and 4 to 9 you go by 5, and then 9 to 16 you go by 7. So that's where the odd numbers come from And that's why the parabola takes that shape. Because for every unit that you move to the right, you're going up by an odd number in that sequence.
And it's always like
It's always like that. Yeah. Well, there's an unless. But yeah, a standard parabola. This is a standard parabola. What makes it a standard parabola is that there's a 1 in front of the x squared. So long as it's a 1 in front of the x squared, that's the slope of it. Okay, that's the first thing I wanted to tell you about graphing a parabola. The second thing is now to take a look at this transformed formula and say, well, what do these things mean? If you have a number being added outside of the x squared, right? So you have some component here, which is something being squared. If you add a number outside of the function, and as an example, that would be like x squared plus 5. Okay, the 5 is being added outside of the squared component. Then that is a vertical movement. It moves the parabola up and down. So the vertical motion is up and down. And it does so just like you'd expect. If you add a number, you go up, and if you subtract a number, you go down. So for instance, in the parabola x squared plus 5, you take the standard parabola, which starts at the origin, and you simply shift it up 5 units. So this would be a standard parabola, the one we just graphed, and then you shift it up 5 units. If I had the equation x squared minus 7, you take a standard parabola starting at the origin, and you'd shift the whole thing down 7 units. So that's what the number outside of the x squared term, what it does.
So the answer to the first one is B then.
Yeah, the answer to the first problem is B. Do you guys see that? The first problem is x squared minus 3, so therefore you just take a standard parabola, shift the whole thing down 3 units, and the answer is definitely B. This graph right here, if you just label it, go ahead, is x squared minus 3. You could probably go ahead and tell me the formula for D then. What's the actual formula for the parabola in D?
X squared plus 3.
Yeah, x squared plus 3. Now what about the formula for A and C? These graphs have been shifted not up and down, but they've been shifted right and left. So that's when you add or subtract a number inside the component that's being squared. So if on the inside of the function, you know, the thing that's being squared, if you add or subtract a number, we're going to call that inside. That describes the horizontal motion.
Oh, that's like an H.
Yeah. Well, no, actually, I don't think the H stands for horizontal, but that's a really good way of thinking about it. And of course, that would make sense that K then stands for vertical. No, it doesn't.
Oh, I don't know.
Or vertical. Yeah, I don't know. That would be nice if it was H and V. For horizontal
Yeah,
and
why
vertical.
wouldn't it be?
It's unfortunately not. It's a historical thing. They just used H and K. It's terrible. All right, so the horizontal motion, the only difference now is that it's the opposite of what you'd expect. So even though you're going right and left, right is actually given by subtracting a number, and left is actually given by adding a number. So that's the opposite of what you'd expect. So if you're adding or subtracting a number inside the thing being squared, it's the opposite of what you'd expect. Whereas if you're adding a number outside the function, it's the same as what you'd expect. That up is positive and down is negative. But if you're adding or subtracting a number inside, plus means go to the left and minus means go to the right. That is opposite of what you'd expect, right? Because on a graph, plus means right and minus means left, but not so in this case. Was it? Yeah, that'd just be too easy. So given that, folks, what would the formula here be? It'd be y equals x something squared. Since we moved left 3 spaces, it's going to be x plus 3 squared. That'll be the answer for A. That function that's graphed in graph A is squared. You'll notice it's still the standard parabola. If you get in there and look at the dots, you start at the origin, and then you go right 1, up 1, and then right 1, up 1, 2, 3, and then right 1, up 1, 2, 3, 4, 5. So it's still following the standard parabola of 1, 3, 5. The only difference is that I just shifted the whole parabola to the left, and we denote that by writing x plus 3 squared. What would the formula be for the graph in part C? Yeah, it'd be y equals x something squared. Since I shifted right 3, you write minus 3. All of those parabolas, however, are standard slope. If you look at each and every parabola and go to the vertex, it would be right 1, up 1, right 1, up 3, right 1, up 5. So all the parabolas are the standard shape. They've just been.
The slope.
What's that?
A is the slope.
A is the slope. Yeah, absolutely. A is the slope. The first thing you want to know about A is that if it's positive, the parabola is facing up. Right? Whereas if it's negative, what? Yeah, it's facing down. And then more importantly, the A value, if there is an A value, then that is going to tell you how to change the standard slope from 1357. It becomes 1A, 3A, 5A, 7A. You actually just multiply the sequence 1357. You multiply each number times whatever the value A is. So for instance, if I had given you the graph y equals 2x squared, instead of doing a standard slope of 135, you would multiply all those numbers times 2, and it would be 2, 6, 10. And that would be how you graph the parabola. We're going to do examples of that. We haven't just yet. Hey, Esther, I don't know if you have a packet for chapter 10. Let me give it to you real quick so you can. Oh, you might have. Okay, well, great. Well, here, in any case, I'm going to. Yeah, I'm going to hand you. There you go. All right, well, folks, those are the rules. What I've written down right here, that is how you know the formula for a parabola just by looking at the graph. Or alternately, if someone gives you a formula, that's how you know where to graph the parabola, is according to those rules. So we certainly did this problem. All they were looking for in this problem was just to say which graph is x squared minus 3, and that was B, right? Yeah. Okay, well, that's that. Now, you might be wondering, why is it that the inside one is opposite of what you'd expect?
Is it the squaring?
Is it because of the squaring?
Like negative 10 to negative, is it positive?
Maybe. That's a good guess. I don't think that's it.
Okay.
Yeah. But let's wonder, what we're looking for is the location of the bottom, right? We're looking for the location of the vertex. And we're wondering, how do you move that vertex around? It's kind of like pin the tail on the donkey. Can you imagine that the vertex is the tail on the donkey, and you're really picking up the vertex and moving it right and left and moving it up and down? So we're wondering, where's the vertex? Well, the vertex is the lowest value, right? It's the smallest value. I shouldn't have erased my table of values. And what's the smallest number that can be squared? Yeah, like if I look at all these values, negative 1 squared is 1, negative 2 squared is 4, negative 3 squared is 9. What's the smallest value you get as an output? Definitely 0. 0 is the smallest value. And so that would represent the bottom of your parabola, right? The bottom of the parabola is whenever you are squaring an input of 0. So in this particular problem, how do I make x minus 3 equal to 0? Yeah, I move that 3 over, and that means that the bottom of my parabola will occur when I plug in 3. And sure enough, where's the bottom of the parabola? At 3. That's the explanation for why it's the opposite of what you'd expect. Because you're really wondering, what value would I have to square to find the bottom of the parabola? I'd have to square 0. And when is x minus 3 equal to 0? When x is 3. So that's what changes the sign from negative 3 to positive 3. And that's why we look at the opposite value. Maria, what do you think of that?
Better answer than mine.
Okay, well, yours was a nice guess, though. Really was. Okay.
I figured that would be 2.
Yeah. Let's keep going, and I'm gonna keep my little notes up there on the board so you can continue to reference them. Hopefully you have them written down too, but we're about to turn the page like that. So let's try the next one.
So what if it's written out like a 2x squared plus b, or plus 3?
Well, like if you FOIL the whole thing out?
Yeah, it's
That's
not,
totally different.
Okay.
We'll get to that.
Okay.
Yeah, we are gonna get to that today. Okay, so let's go ahead and take a look at these next few formulas, folks. It says here, identify the vertex of the given parabola. Well, the vertex, I should go back to my example here. The vertex is the point that has been moved around, right? So when we're looking for the vertex of the formula, the vertex is actually just the value of h and k. The vertex is the value hk. because that will tell you how far was your vertex moved right or left, and how far was your vertex moved up or down. So the value hk is the vertex. That is the lowest point of your parabola. So let's practice that a couple times. It says you identify the vertex of the given parabola. I'm going to write it down again here, and I hope you write it down as well. The vertex form is y equals a x minus h squared plus k. That's the vertex form, and the vertex is the coordinate hk. Now you'll notice what happened to the sign of h. Yeah, well, it changed. Yeah, it went from whatever, if it was a -3, then it would become a +3, or if it was a +2, it would become a -2. So h, you take the opposite value of whatever is inside the parenthesis, but k, you take the same value. And you might even want to write that down. That h, from the formula, you take the opposite, and k, from the formula, you take the same. So, looking at our very first example here, this is the function of a parabola. You know it is because it's something squared. And this -5 means technically what? -5 means which way did you move, right or left? You went to the right 5, and the -5 outside here, since it's outside, what does that mean? Did you go up or down? Down 5. And so technically, if you're on a graph, and you went right 5 and down 5, where's your vertex? That would be the coordinate 5, -5. Right? The vertex got moved right 5, down 5. And compare these two numbers. The x-coordinate, even though in the formula it's -5, the x-coordinate is +5. And in the formula, the y-coordinate is -5, and sure enough, it is still -5. So the vertex, in this case, is 5, -5. And you can see that very quickly by just taking the opposite of the number inside the parenthesis and the same value as the number outside the parenthesis. Does that make sense? Okay, well, let's try the next one then. Here we have just x squared plus 2. So since it's just x squared, did your parabola move right and left at all? No, it didn't move right or left at all. And then did it move up or down? It moved up 2. So simply speaking, that means that you took your vertex from the origin and you just moved it up 2. And that would be where your parabola is. And therefore the vertex is at the coordinate 0, 2. And you can see that a little better. This might seem arbitrary, but I could rewrite x squared plus 2 as 1 times x minus 0 squared plus 2. Why would I rewrite it as 1 times x minus 0 squared plus 2? Because then it looks exactly like vertex form. That shows me that my a value is 1, my h value is 0, and my k value is 2. By rewriting it kind of in an expanded form. So taking a look at the next one, number 60, is this already written in transformation form? It looks like there's one more number I could write down. The 1 in front. So here I have my transformation form. This is really a x minus h squared plus k. So that's a parabola in transformation form. And so if you want the vertex, well, first let's talk about which way it moved. The x plus 4 means it moved what, right or left? Left, because it's opposite of what you'd expect. Left 4. But there's a plus 7 outside. Does that mean you move up or down? That's up. So our vertex moved left 7 up, no, I'm sorry, left 4 up 7. And so if you imagine on a graph, you take your vertex, you move it left 4 up 7, and your vertex would be up here. So your parabola would actually be up there because you went left 4 up 7. And what is that coordinate? Yeah, the coordinate's -4, 7. And I think the best and fastest way to see that is just to take the opposite of the number in the parenthesis and the same value of the number outside the parenthesis. So you can do it both ways. You can memorize it as a rule. You just take the opposite of the number in the parenthesis and the same as the number outside the parenthesis. Or you can think about what that means. The plus 4 means left 4, which is literally left 4 in the coordinate. And the plus 7 means up 7, which is literally up 7 in the coordinate. Okay, everybody try number 61. What is the vertex of that particular parabola? Where is the vertex of that parabola? Yeah, -6, -9. And you can read it. This is plus 6 means left 6. And the -9 means down 9. And literally, if I go left 6 and then down 9, my vertex is way down here. That would be my parabola. And the location of that vertex is indeed, well, I have nowhere good to write it. It would be -6, -9.
Yeah, so there's a number in the front of the parentheses,
Yes.
and that's negative.
To flip it upside down? Yeah, to flip the whole parabola upside down. Yeah. Well, folks, now that we've talked about this, I feel like I really just jumped in here. I might not have motivated this properly. We've been looking at how to solve quadratics, but we haven't really looked at how to graph quadratics. So that's what we're talking about today is how do we graph a quadratic? And the most convenient way to graph a quadratic is in this transformation form, because just by looking at the 3 numbers in the formula, it tells you where and how to graph your parabola. Yeah.
So left is negative.
Yeah, left is positive, right is negative, and up is positive, and down is negative. Yes, absolutely. Yeah, this, I did intend for you to write down, yeah. Yeah, those are good notes right there. Yeah.
Okay, so this is probably silly, but when would you want to see it in picture form?
When would you want to look at it?
Yeah.
That's a good question. Like, what if you were doing a word problem and you threw a ball,
Okay.
and you just wanted to know the entire flight and curvature of the ball? Then you could see when the ball was its highest and when the ball landed and, you know, when the ball was still on its way up. Like, you might want to look at a graph.
Okay.
Yeah. Yeah, so all of this is just to get a good look at it. Now, of course, these days, folks, how would you graph any function?
On a calculator.
Yeah, on a calculator, right? You would just go to your calculator or Desmos. And what was that very last formula there?
X plus 5 parentheses squared, that one? Or the other
No,
one?
the very last one. Wasn't the very last one?
X plus 6 squared.
Yeah, there we go. So x plus 6 squared minus 9. So was it true? Did the vertex, was the vertex at -6, -9? Yeah, the vertex really was down there. Maybe I'll put it up there so you can see it. And transformation form is just a really fast, shortcut way of knowing where to place your parabola. Of course, what if you didn't have a graphing calculator and you didn't know transformation form? How would you ever know what the graph looks like?
You would input values.
Yeah, exactly. You would do a table of values, right? You'd have your x plus 6 squared minus 9. You would just have to sit there and do a table of values to figure out where all the different coordinates were. So let's just say that I chose -7, -6, and -5. I would plug those in. -7 plus 6 is -1. Squared is 1 minus 9 is -8. And then -6 plus 6 is 0 squared, which is 0 minus 9 is -9. And -5 plus 6 is 1. 1 squared is 1. 1 minus 9 is -8. And now I would have 3 coordinates, and I would go to my graph, and I would actually plot them out as 1, 2, 3, 4, 5, 6, 7, down 1, 2, 3, 4, 5, 6, 7, 8, 9. And look at my first coordinate, 1, 2, 3, 4, 5, 6, 7. Down 7, I'm sorry, left 7, down 8. Left 6, down 9. And left 5, up, down 8. There. Do you guys see the beginning of my parabola down here? Everybody? Hello? So if you didn't know transformation form and you didn't have a graphing calculator, you would just have to start plugging in values until you could start to see where your graph is. But nobody wants to do a table of values to graph something because it's so time consuming. So rather than doing a table of values, if you didn't have a calculator, you would want to know transformation form, which is what we're talking about. There, that's everything I should have said right up front. So let's go ahead and turn the page and try it. Now that we have all of our skills, we can put them all together, and we can be a graphing calculator. So it says sketch the graph of the parabola. Now, if you didn't know transformation form, you would have to do a table of values. And a table of values, that'd be very time consuming. So that would be what you could do. But instead, now that we know the definition of transformation form, where's the vertex of our parabola? It's at the coordinate what? Negative 5, 6. Yeah, opposite same. That's always what it's going to be. It's going to be opposite same. So our vertex is located at negative 5, 6. So we go ahead and go on your graph to negative 5, 6, which is here. So that's your vertex. And now you count out the standard slope, which is the odd numbers, 1, 3, 5, 7, and so on. You really just do as many odd numbers as you can fit on the graph. So starting from the vertex, you go right 1, up 1, right 1, up 3, right 1, up 5. And that's as far as I can go. So then I would go left 1, up 1, left 1, up 3, left 1, up 5. And that's as far as I can go. And that would be your parabola. Which is just way more time efficient than doing a table of values.
When you go there,
How do you what?
you call your
Oh, well, this I gave to you as the definition. This is the slope of the standard parabola. So if you're just looking at a standard parabola, and by a standard parabola, I mean the fact that there's a 1 in front. So long as there's a 1 in front, the standard parabola goes like this. You're always going right 1. So right 1, right 1, right 1. So you go right 1, up 1, right 1, up 3, right 1, up 5, right 1, up 7. So these are your up numbers. Maybe I should tell you that. Those are the numbers by which you're going up. Every time you take a step to the right, you do the next number in the sequence. So, Amy, thanks for asking your question. You mean the slope again or the vertex? Oh yeah, so it's 1, 3, 5, 7 provided the number up front is a 1. Like, you know how whenever we were doing factoring problems, we always hoped that you were factoring a problem that had x squared with a 1 on it? We always preferred x squared with a 1 on it. And that's what we're really talking about, is that so long as x squared has a 1 on it, which is this case, it just takes the shape of the standard slope. Okay, so now, Azem, you were just saying, how does it work? So from your vertex, you got your vertex? Okay, so you're going to go right 1, up 1, put a dot. And then from there, from that dot now, you're going to go right 1, up 3. And then from there, you're going to go right 1, up 5. And then from there, you go right 1, up 7. And that's how you keep on putting dots. Thank you, Azem, for asking me to clarify that. Now, that's just going to the right. You're now going to do the same thing going to the left. So starting again at the vertex, you'd go left 1, up 1. And then from there, you go left 1, up 3. And then from there, you'd go left 1, up 5. And from there, you'd go left 1, up 7. And you'd see your parabola now taking shape. By the way, folks, what does vertex mean? What is the vertex? It's the bottom of the parabola. It's the point that's at the symmetric middle of the parabola. It's not on the right-hand side, it's not on the left-hand side, it's right in the middle. Okay, I'm sure you're all wondering if the table of values would have given me those same coordinates. You're all wondering that? You're all, oh, but I wonder, would the table of values have given me the same coordinates? Well, that's a good question. Well, my vertex I can see is at -5. So I'm going to try some values to the left and right of -5. There, so I've got some values to the left and right of -5. So if I plug in -7, -7 plus 5 is -2. 2 squared is 4, 4 plus 6 is 10. And then -6 plus 5 is -1. 1 squared is 1, 1 plus 6 is 7. And -5 plus 5 is just 0. 0 squared is 0, 0 plus 6 is 6. -4 plus 5 is 1, 1 squared is 1, 1 plus 6 is 7. And -3 plus 5 is 2, 2 squared is 4, 4 plus 6 is 10. So are those the coordinates that we just had? Are those indeed the coordinates that I plotted on the parabola? Well, sure enough, there's the vertex, -5, 6. And then here's the coordinate -7, 10. So that was there. Here's the coordinate -6, 7. Here's the coordinate -5, 6. And the coordinate -4, 6. Sorry, 7. And the coordinate -3, 10. So does the table of values line up with the standard slope? Yeah. So now that we've seen all this, what is the point of transformation form? What is the point of learning this? Yes, it is easier to graph. That's exactly right. Transformation form, the whole point of memorizing the way this works is so that you don't have to do a table of values. It just saves time. Believe it or not. Isn't that funny? There's a paradoxical nature of knowledge here. It takes time to learn new things and definitions and how the rules work. But then once you do, it saves you time because you don't have to do all this plug and chug work later on. So there's an upfront investment of learning this, but then after that, it's very easy to do all of your graphs because you don't have to do tables of values anymore. All right, well, I think that's it for number 62. Let's try another one. Oh, actually, those are the only examples that I have. So that's how transformation form works. Now, before we move on, is there room right there? Hold on, go back a page. Nah, there's really not room right there, is there? That's okay. We're gonna do a problem at the bottom of the page that I made up. So we have the next page has numbers all the way through 66. I would like to make up a new problem on that page, and I'd like you all to do it with me. You're gonna be really impressed. You're gonna say, wow, this is fun. So just come down here to the bottom. You'll have a lot of room down here at the bottom. And everyone write down the function x squared plus 6x plus 10. Is that transformation form?
No.
No, it's not transformation form. So do I know where that graph is? No,
Not yet.
I don't know where that graph is. Can I factor that graph? Anything multiply to make 10 that adds to make 6? No. Could I use the quadratic formula to find the roots? Yes, I could. The key thing is, though, right now we have no idea how to graph this thing, right? Well, how do I transform this into transformation form? What's the key thing that transformation form has? The x minus h squared. And we get that by completing the square. So everybody, let's go ahead and complete the square on this thing. We're going to do it slightly differently than before. What I'd like us to do is write down x squared plus 6x, leave a space, and then put the 10 at the end. What would I like to add to 6x so that I can rewrite so that this thing is a perfect square trinomial? Not 12. Remember how it works? You take the middle term, divided by 2, which is 3, and then you square it, which is 9. So what number do I want right here? Plus 9. Now, if I'm going to write a plus 9 right there, I can't just add 9 to one side of the equation. I also have to subtract 9 so that I balanced it out. Does that make sense? All of this is happening on one side of an equation. And so I'm saying if I arbitrarily add a 9 here, I have to subtract a 9 so that it's still equal. You know, the plus 9 and the minus 9 cancel each other out. Okay? Okay, so how can I rewrite x squared plus 6x plus 9? That's really what?
X minus.
No, not minus.
Oh, plus 3.
Yeah, plus 3. That's the number right there. X plus 3 squared. And then what's this part now? 10 minus 9? 1. Oh my gosh, what's that? That's transformation form. Right, now I can look at that, and where's the vertex? Yeah, my vertex is now at negative 3, 1. And it's a standard parabola, and I can go ahead and graph it. So I could go to negative 3, 1, put my vertex, and I could go right 1, up 1, left 1, up 1, right 1, up 3, left 1, up 3. And that would be my parabola. So how do you take any ax squared plus bx plus c, any quadratic formula, and turn it into transformation form? What do? And you complete the square. Isn't that the formula? That's the process we're doing, completing the square. So you complete the square, and that will turn it into transformation form. Completing the square, yeah. Okay, so I just wanted to show you that real quick. The transformation form is not far away. We can all take any formula and convert it into transformation form just by completing the square, and then you can graph it. That is provided that it's easy to complete the square. Remember, to complete the square, what do you need the number on x squared to be? 1. That makes it the most easy. So now look at these next few problems that they gave us. Are these easy to complete the square? No. These are not easy to complete the square at all. So it would be nice if there's another way to know where the vertex is, other than completing the square. And remarkably enough, there is another way. And so I'd like us all to take notes up at the top. It says find the vertex of the given parabola. Go ahead and take these notes with me. If they don't give it to you in transformational form, and it's hard to complete the square and convert it into transformational form, you can just say, given the function f of x equals ax squared plus bx plus c, the vertex is the x-coordinate of the vertex is negative b over 2a. That is just straight up the formula for the vertex. That is the x-coordinate. I didn't tell you the y-coordinate just yet. I'll tell you the y-coordinate in a second.
That looks super familiar.
Does it look familiar? Negative b over 2a? It does look familiar. You've all seen negative b over 2a before. I'll go ahead and suggest it to you. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Where's the negative b over 2a?
First half of it.
Yeah, right there. The negative b over 2a. And in fact, what that states is it's negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. So in fact, the very first term of the quadratic formula is in fact the vertex of the parabola that you're graphing. So every vertex of every parabola takes place at the x-coordinate, negative b over 2a. Just for funsies, everyone go ahead and say negative b over 2a. Everyone go. Negative b over 2a. It's a really good thing to put in your mouth so you memorize it. Negative b over 2a. So that's our formula for the vertex. Let's go ahead and find the x-coordinate of the vertex of that first function. Now remember, this is last resort, right? Hopefully they already gave it to you in transformation form. And if they didn't, you can complete the square and turn it into transformation form. But if you get a quadratic that's looking pretty nasty and you don't want to do any of that, then there's simply a formula, negative b over 2a, which you can always remember because it's the first term in the quadratic formula. So let's go ahead and find it. This quadratic, which I would like to graph, but I don't know where to graph it, the vertex is, well, first of all, I'm going to write down a is 3, b is 24, and c is 51. And so the vertex is negative b over 2a. And as before, I recommend you write that empty. How would you write that empty? Negative parenthesis over 2 parenthesis. That way you can drop in your values. So b was 24 and a was 3. And what does that give us? Negative 24 over 6, which is negative 4. Okay, well that tells us something. We now know that wherever this parabola is, the vertex is over the x location, negative 4. Is that fair? That maybe the vertex is here, and there's the parabola. Maybe the vertex is here, and there's the parabola. Maybe the vertex is here, and there's the parabola. Maybe the vertex is here, and there's the parabola. We don't know where up and down the vertex is, but we do know that the vertex is somewhere along this vertical line of -4. So I'll just put one little sample drawing. Maybe that's where the parabola is. How do we calculate the y value? Now that we know the x value of the vertex, how high up or down is it?
My guess is it's the other half of it.
Oh, now that's very interesting. The other half of the quadratic equation is telling you, and I'm glad that you asked that because that was a fun guess. If you actually look at a parabola and the vertex is down here, you've got this. This is the location of your vertex. This and this,
Oh, those are.
that's the plus and minus. That's to the right, go
Right.
to the right that much and go to the left that much. So that is the distance, the horizontal distance is, that's plus root b squared minus 4ac over 2a. And this distance to the left of the vertex is the minus b squared minus 4ac over 2a. So that was a really good guess, but the b squared minus 4ac over 2a tells you how far do you go to the right and left of the vertex to find your x-intercepts. So this part, this is definitely the vertex. Negative b over 2a is the vertex. And the b squared over minus 4ac over 2a, that's telling you how far right and left from the vertex you go to find the x-intercepts. So no, that's not going to tell us the location of the vertex. You would like to think it has to do something with the c value, right? Because we haven't done anything with it yet. Those are really. Oh, now that's a really good thought. Since the c value is the plus c at the end and the k value is the plus k at the end, maybe the c tells you, where the location of the vertex is. It's a really good guess. Unfortunately, it's not it.
But I would think, like, if you knew one of the numbers and you knew the two places that it intersected, you should be
Able to
Golden.
calculate.
Yeah.
Getting close. Well, here's the ultimate answer. You just take your x-intercept and you just plug it into the function to calculate the y value. After all,
that's way too much.
yeah, after all, folks, remember this f of x, this is really y equals 3x squared plus 24x plus 51. And since we already know the x value of the coordinate is -4, how do you calculate y? The function itself calculates y. So now what we're going to do to find the, and I'll finish the formula now. The full formula of the vertex, the x coordinate is negative b over 2a. The y coordinate is the function evaluated at negative b over 2a. You just plug that value into the function and it will tell you the y coordinate. So let's do that. Let's plug -4 into the function. So that's 3 something squared plus 24 something plus 51. This is going to calculate our y value. Even write it out, y equals. So let's plug in, not 3. Oh, the answer is 3. You already did it. Yeah, let's plug in -4. And when you plug in the x value of the coordinate, that'll be 3 times 16 minus 96 plus 51. That's 48 minus 96. Really? So that's 99 minus 96. Oh yeah, sure enough, it's 3. So now we know that our vertex is at the location -4, 3. So we would go -4 up 3, and there's our vertex. That was 2 very different steps. Right? So like if we want to write down the steps, step 1 is the x coordinate of the vertex is negative b over 2a. The y coordinate of the vertex is the function evaluated at negative b over 2a. Meaning you plug that x value into the function and that will tell you the y coordinate. Yep. Yeah, exactly right. And then, well, yeah, and then to graph it, because there's a 3 on the x squared, you would take your standard slope of 1, 3, 5, 7. It would actually be 1a, 3a, 5a, 7a. And that would tell you how much to put your slope in.
Are you sure? Because, well, I'm sure you're pretty sure, but
Thank you, Robert.
never mind.
But yeah, there's definitely gonna be a 3 out there.
Doesn't the 3 have to come out of plus? Like,
It does.
I'm like, because it should be 3 times x squared. Like,
Yes.
word.
And in fact, no, thank you for asking, Maria.
Okay.
And we'll definitely demonstrate it here. Let's say that you did want to complete the square. 3x squared plus 24x plus 51. It just so happens those are all divisible by 3. So we could go ahead and complete the square. I'm going to bring a 3 outside. So that's x squared plus 8x plus 17.
Okay.
Everyone, you might want to do this with me just for fun, showing how to do completing the square in this way. We're going to take, so now that we've just proven to ourselves that the vertex is at -4, 3, let's take 3x squared plus 24x plus 51 and actually complete the square and turn it into transformation form. So you start by factoring out the 3, because now you know that that 3 is the number out front. Now, this is a little different from how we've completed the square in the past, so everybody write it down like I do. I'm going to leave some space, and then write my plus 17, and leave some space again. I don't have to do that. No, it's okay. We're going to do it this way. So complete the square. What number would I add so that I'm completing the square?
8 by 2 squared is 16.
Yeah, 8 over 2 is 4. You square it, and that's 16. So we're going to add 16. But within this parenthesis, if I add 16, I also have to subtract 16, so I'm not changing the value of anything. That might feel weird. This is something brand new. We're just trying it today for the first time. We're taking a set value, and if we add 16 to it, we have to subtract 16 from it, so that we're not actually changing the value inside the parentheses. That's what we're doing right now. When I'm done, when all is said and done, I need this thing to add up to x squared plus 8x plus 17. And does it still add up to x squared plus 8x plus 17? Yes, because the 16s cancel out. Okay, so now we have 3 outside of, what does this part rewrite into? X squared plus 8x plus 16, that's x plus 4 quantity squared. But then I also have now, what's 17 minus 16? Just a 1. So now I have 3 times x plus 4 squared plus 1. That's not the end of it. We'll go ahead and allow the 3 to get distributed to both the parenthetical and the 1. And your final answer is 3 x plus 4 squared plus 3. Again, that was a slightly different technique than we did before. If that felt a little uncomfortable, that's okay. We can always do another one. In any case, what is the vertex of this transformation form? What is the vertex?
4.
-4, 3. Is that what we got from the formula?
Yes.
It is -4, 3. So what I hope to demonstrate from this is that there is a formula that will just tell you the vertex, right? If you're just given a quadratic, there's a formula. It's -b over 2a. You calculate that, you plug it into the function, and whammo, you just know the vertex. That is, if you don't want to go through all the bother of completing the square.
Okay, so the answer, whatever's multiplied at the beginning is always the slope.
Yep.
No matter.
Yep, the number on x squared is definitely the slope, which you can here and see. Everybody, I'm just guessing. Okay, looking at facial expressions. Was there something uncomfortable about the plus 16 minus 16? Okay, why do I add 16 and subtract 16 in the same breath? Yeah, what if all I did was just add 16?
Didn't have equal to plus 16.
I mean, if I just add 16, I just changed the equation. I'm not allowed to just randomly add numbers to things because then I changed it. So since I added 16 to it, I also have to subtract 16 to it because a plus 16 and a minus 16 cancel out. Now, folks, can I do that again with you real quick? Everyone watch, because you might prefer this. You might prefer this. Let's say that I have here the x squared plus 8x, and I know I want to complete the square, but overall I have a 17 here, right? I have a 17 here. So what number did I want to add here for completing the square? Half of 8 is 4. 4 squared is 16. I'd want to add 16. Well, I had 17 available. So if I just put a 16 here, what other number would I have to put there?
+1.
Plus 1. So that's another way I could have done it. I could have taken the 17 and just apportioned it into the part that I want for completing the square. Does that sound better to you? Do you really? I mean, you can. The only thing is, what if this was a negative number? You'd have to do some fancy thinking about what the other part was. Whereas by simply writing down the 17 and saying, well, I know I want to add a 16, so I have to subtract a 16 so that I don't change the value, that still gives you the perfect square, and 17 minus 16 is still 1. It just depends on how you want to think about it. Okay. All right, well, let's go ahead and try another one, folks. That was a good problem because we were able to see it both ways. We got to see it from vertex form, and we also got to complete the square. Goody gumdrops, we get to do both ways with this one as well. Because what do you notice about the 4 and the 8?
They're both visible.
They're both visible by 4, so you can factor that out and you can still complete the square. So first, let's try the vertex formula. What is the vertex formula? Yeah, negative b over 2a, and then whatever that is, you plug it into the function, and that will give you the y value of your vertex. So there's our vertex. I'm going to go ahead and write down that a is 4, b is what? Then negative 8, and then c is 9. Do you feel bad for c? No, because we don't seem to be doing anything with c. At least not when we calculate the x-coordinate of the vertex. So the x-coordinate of the vertex, I'm going to go and do this one. Negative b over 2a. I'm going to write it empty. Negative parenthesis over 2 parentheses. I'm going to plug in my numbers. B is negative 8. You notice how important it was that we wrote that empty with the negative sign out front? Because it's a double negative. Over 4. So what do we end up with?
1.
Yeah, actually, a negative, double negative is plus 8. And over 2 times 4 is another 8, and that's 1. So the x-coordinate of the vertex is 1. So I'm going to go ahead and say the vertex so far is 1 comma something. Okay, so now how do I calculate the y value? Yeah, the formula itself is my y value. So now y is 4 something squared minus 8 something plus 9. And for that, I'm going to plug in the x value of the coordinate, which is 1. And that's going to calculate the y value. So that'd be 1 squared is 1, so 4 times 1 minus 8 times 1 plus 9. That's really 4 minus 8 plus 9, which is what?
5.
Yeah, 5. So now the y value is 5. Now, folks, do you want to see something that might feel like cheating? What if now I told you, let's complete the square to rewrite the formula in transformation form? So what if I said, I want to take the formula y equals 4x squared minus 8x plus 9, and I want to complete the square and end up in transformation form. You all can go ahead and tell me what transformation form is going to be. It's f of x equals what? What's the number up front? Hold on, I'll write it down. A x minus h squared plus k. What will be the number up front?
Which is 4.
4. And what's the number inside my parenthesis? Since my vertex is 1, 5. Yeah, x minus 1. And then my k value? Yeah, see there, I already kind of knew what the vertex form was going to be. Because we knew what the a value was. The a value was the 4 out in front. And since I knew the vertex from the formula, it was 1 and 5. Minus 1 and 5. Well, that's a good point, Jordan. Why would you do it? Just for the sake of doing it.
You need to check your answer and see if it's right.
Yeah, but here's the thing. I know my phone just went off, so we'll take our break. But right after we complete the square. Everybody, let's complete this square one more time. Because we've now completed the square twice. If we complete it one more time, we'll feel a little more comfortable with this method. So the first, I feel a little tempted to show you a slightly different way.
Yay.
I think you might like it. Everyone, go ahead and rewrite 4x squared minus 8x and leave a little space and write the plus 9. And what we're going to do is treat this as our complete the square portion, and just leave the 9 out there. Just leave the 9 out there. So the first thing we have to do is factor the 4 out. So that's going to be 4 outside of x squared minus 2x something plus 9. Is that still fair? So now let's complete the square inside. If we complete the square, what's the number we have to add? You take half of b, so negative 2 over 2 is negative 1, and then you square it, and that gives you 1. So we're going to add 1. But if you're going to add 1 inside this parenthesis, you also have to subtract 1. You're not allowed to just add a number somewhere, because that changes the value of the function. You have to add 1 and subtract 1. And we're going to wrap our parentheses around this one, the x squared minus 2x plus 1. There's also a little minus 1 up there. So now what do we have? We have 4 outside of, what was x squared minus 2x plus 1? How can we rewrite that? Yeah, x minus 1 quantity squared, and the little minus 1 that we wrote, plus the 9. And then we have a 4 outside of the x minus 1 squared and the minus 1. We have to distribute the 4 to both of those values. So that'll be 4 times x minus 1 squared. And then 4 times minus 1 is minus 4. And then the plus 9. And what does that give us? Did it work? It gave us the transformation form. Going back to Jordan's question, why would you want to do that? Yeah, you very well could be running out of room. You know, we already have this formula that tells us how to find the vertex. I guess, you know, my real goal here is to show you that we're talking about all the same stuff. You can either take a formula, complete the square, put it in transformation form, and that would tell you the vertex of 1, 5. Or you can just take your formula, run it through this formula of negative b over 2a, and that would tell you your vertex. So you have 2 different options for finding the vertex of your parabola. And once you know the vertex, all you need to know is the slope, and then you could actually draw that parabola. All right, well, I can tell by the way these problems are written. You notice the first 2 numbers are both divisible by 3, and then here, the first 2 numbers are both divisible by 4. What they want you to do is complete the square. What they'd like us to do is complete the square. Jordan, let me see your paper. You're saying you're almost out of room?
Yeah, but I write really big, so
I think we could still do it, because doing the formula is super easy. Negative b over 2a, we can do that no problem. I would like to practice completing the square with you 2 more times, just so we feel really comfortable with it, and then we'll move on to something else. But for now, let's take a break. It's 2:04. Let's start again at 2:14. Oh, yeah. What is it? Oh, it's your extra credit. Okay, great. Thank you. Yes. You go ahead and take a break. I was gonna say. Oh, so you're leaving this one. Oh, okay. Well, then we'll do another day. Yeah, sure. Yeah. I mean, I'll just go ahead and do, these are just, this is just technical. And then these were some of the notes from other classes that have been. Let's just meet, what other day do we meet? Roughly 10:30 to 11:30 to 2:30. We do a Thursday class? Oh, sorry. So you're saying every Tuesday, Thursday, pick one, 2:30. So you're yeah. So in other words, you're not going to catch the whole class. But I am recording this. Have you already watched all of the videos? Okay, so that would be the first step, to go back and watch all the 15 minutes. Because I recorded them all for you. Yeah, that was for you. I recorded. Okay, all right. And so we'll just find a time to make sure you have all good. Okay, yeah, go this way.
I'm wondering if you're
What are you doing there, Corinne? Oh, okay. Claudia, Jeffrey, Zed, Amy. Yeah.
Oh, too big. That's why I like exercising, because being in the gym, like you never feel like you're fat.
Like I got steak last week and I went to the gym at 9:00.
Was it fun?
That's what I was all about. Like, this was like I'm on a date the whole time. But then I'm like, oh, I'm sick.
Huh, NyQuil, huh, the secret to exercise.
No, just kidding. Don't do that. That's because I was sick. And I was still trying to
Miss
get
the
my
gym.
workout on.
Maybe,
But, oh, and it's all about like strategy too, like as far as like drinking lots of water and like eating at certain times and then like, not eating like.
for some reason, you just feel better about yourself when you're exercising.
Well, whenever you're like crazy, that's all. And like now I like I've been crazy for like almost 2 years. Oh man, I wish my mom was doing this.
Are you doing like the Zumba? Yeah. Have you seen that, what's that new dancing thing with the fitness? I can't remember what it's called. It's one of those like,
That was the, I don't know what it's called, but I'm like, I can't wait to get like, to like a lower size, see my buy some really nice clothes. So I don't wanna go shopping until I get to it. Like, no more shit, I'm not having anymore, so I'm like, all happy.
Great.
Done, 'cause I had two and I'm good. So I'm like, trying not to have it, just like, you know what I mean, and like gaming and then like.
Evolve.
So.
That's it, evolve.
husband's sick right now, so like I laid out like a whole bunch of stuff on the bed, and then I made him like ramen, and then like I got a soda, and I'm like, you take these next meal, and then I gave him some chips, and all he drinks is soda, he doesn't drink water. So I gave him that or whatever, and then he sat on the couch, ate his lunch. I came out, I was just about to leave. I grabbed him, I'm like, hey, I'm leaving. And then he's like, I'm like, yeah. I'm like, well, I'm not gonna.
Yeah.
I'm like, he thinks he's gonna sleep for all day, right? Because the kids have to get sleep at 4-6. And it's like only a late home at 11. He's like, oh, don't give me that because I'm not gonna wake up. I'm like,
Yeah, that's, I never take that stuff, that's exactly that. I won't wake up.
really?
I will sleep until I am
I
done
can wake up
sleeping.
any morning, like if something's going on.
That is a skill. 'Cause
I think it's because it's just constantly, because he never took care of them and I did. He never fed them a bottle, like never fed them, I like changed them, and I'm just so used to like one little boy to like pet the baby or something. Except
Mine was in high school when I rode on the drum bus. The drum, like while you were trying to sleep. I only got like the hours that you were on the bus to sleep, that was it. So you learn to
why would they
sleep
do that?
because they're practicing. No. I mean, like you'll be on the bus for 12 hours. So like they'll jump for like the first 6 and then sleep for 6 or whatever. You know, I don't know. It was just noisy. No. So I can sleep sitting up. Like people don't know I'm asleep a lot of times. That's just things like I'm hanging out or something, or they won't even look to see if my eyes are closed. I'm sitting up, you know, nobody's still like when they're asleep, like kind of like something. Nope, I'll be like perfectly like tracked, just sleeping.
Oh, it's not a mouth, but my brother was this, so. So it'll be fine. So like Steven, I gave him that pill, like, just wake him up so he doesn't get late to pick the kid. For now. He's gonna last for like a year. Well, this month it'll be a year. But I don't care. He needs it. I'm not fishing him out anytime soon. But if you start getting a serious girlfriend, family, you can still find a house.
Right.
Because I can't do all my family.
No, I can't. I'm going to a movie review.
Only one room available.
I think my kids are okay because I was pushing them around in the stroller last night. and
Yeah, no problem.
My legs are tired. I'm like, what's up with them? I think between the two of them, they've probably gained another 5 to 10 pounds.
Oh, wow.
Like in the past 2
You're
weeks.
getting lots of food. You hear it all there?
They're shooting up.
Tall.
Yeah. Tall. Liam, when we first moved here, Liam was wearing 12 months. That was August, middle of August. He's now in 24.
Oh, wow.
Yeah.
That's good though.
And same thing, Lyric was like wearing 2 Gs and now she's like pretty much in 4 Gs. So I'm like, oh.
All right, folks, let's keep going.
Well, if 3 Gs would fit them with
All right, we're going to practice this technique 2 more times of completing the square in order to change a standard form quadratic, right? This is standard form quadratic. This is ax squared plus bx plus c. And we want to transform that using completing the square. So, what do? We want to complete the square. There's kind of 2 things that are happening, and in fact, the 3 and the 43, I can feel them both kind of pulling towards the opposite directions. What about this 3? We want to pull it out towards the front and factor it out of the 3 and the 24. But we also want to pull this 43 off to the right and kind of separate it from everything else. So let's start by separating out the 43. We've got 3x squared minus 24x. And we're just going to leave a bit of space and then write the 43 at the end. We're ignoring the 43 for a while. We're just going to bring it back all the way at the very end. Right now, we're going to focus on completing the square using that portion. Right? So the 43 we're ignoring. We're completing the square right there. The first thing we're going to do with this 3 is take it out. So you can see we have 3 outside of x squared minus 8x something plus 43. So that, like I said, see that 3 gets pulled out front, and the 43 got pulled out to the back.
It's just, we use those square brackets.
You can do square brackets. In fact, you might prefer the square brackets. Okay, so now let's complete the square. Yeah, you take the negative 8, you divide by 2, which is negative 4, you square it, which is 16. So we're going to add 16, but you simultaneously have to immediately subtract 16. What's that, Olivia? Oh. There's no x to be taken out. No, we're just completing the square. Now, what you might want to do right now, folks, because you just completed the square with the x squared minus 8x plus 16, put a second pair of parentheses right there to note that you completed the square there with the plus 16, and the minus 16 is a separate term that's not part of completing the square. Again, this plus 16 minus 16 might have felt a little awkward at first because we're doing it today for the first time, but this is a really good technique. It's a really good problem-solving technique. By adding 16 and subtracting 16, we technically did nothing, but it's allowing us to rewrite this as a perfect square. So let's write the whole thing again, simply making this as a perfect square. So we have 3, and then x squared minus 8x plus 16 is really what? Yeah, x minus 4 squared, and then I have a minus 16, and then I have a plus 43 left. I think what might make this process feel a little clunky is the fact that we have double parentheses. Right? Double parentheses is not nearly as exciting as a double rainbow. Yeah, I'm sure you've all seen the double rainbow sign, right? Okay, so now what do we do? The last step is to distribute the 3 to the binomial and to the 16. So we go ahead and distribute the 3 to the front of the binomial and to the 16. And that concludes us with 3x minus 4 squared minus 48 plus 40. So what's our final answer? 3x minus 4 squared minus 5? What's our vertex? Yeah, 4, negative 5. That wasn't too terrible. 1, 2, 3, 4, 5, 6 lines of work to get to the vertex. To which you might say, I kind of like that vertex formula. Negative b over 2a. Right? Negative b over 2a I can do in a very small amount of space. Negative b over 2a, where my b value was negative 24, my a value was 3, so negative 24, 3. That's 24 over 6, which is 4. Was the x-coordinate of the vertex 4? Yeah, sure was. Now that I know that my x value of my vertex was 4, how do I get my y value? I just plug it in. So it'd be 3 times 4 squared minus 24 times 4 plus 44. So let's see, that's 16 times 3 is 48 minus 96. Did we already do this one? Gosh, it seems like we already did it. So that'd be 80, 91 minus 96. Oh my gosh, it's negative 5. Was that the y-coordinate of the vertex? Yeah. Okay, so now honestly, which way do you like better? Jordan, I love your honesty. That's wonderful. Jordan prefers this way, folks. Yeah. So, yeah, honestly, obviously, the formula is much faster. Whammo, you do negative b over 2a, that gives you the x value. You plug the x value into the formula, that gives you the y value. So that does tell you. And in fact, since you already know that the first number is 3, once again, once you calculate the vertex, you could just write down transformation form. You just write it down. Because if I were to say, okay, transformation form is a, x minus h squared plus k, I know that my a value is what? 3. And I just calculated my h value, so that's x minus 4. And I just calculated my k value, and that's minus 5. And we still got 3x minus 4 squared minus 5 without doing all that pesky completing the square. But wasn't completing the square satisfying? Maybe a little bit. I mean, completing the square, you should feel like, even if it's a little rusty, even if you're a little like, okay, well, that doesn't make total sense, it's still awfully sophisticated. And you should feel good about yourself for even just being able to follow along, write it all down, and say, oh, yeah, okay, I see all the steps. I might have a little hard time doing it myself, but wow. All right, well, I'm going to leave 66 for you to try on your own. You might notice what makes this problem a little harder. The fact that it's negative. Is that technically going to make the problem harder? No, you just have to be mindful about the negatives. Yes, Amy? Yeah. Oh, put the 16 out there? Now, that's a really good question, folks. Amy asked, since I'm adding the 16 here, can I minus the 16 out here? Why can't you just minus the 16 out here? Yeah, because, Amy, this 16 that you just added is technically a 16 that's being multiplied by 3. So if you wanted to add 16 inside the parentheses, you'd have to be aware of the fact that that 16 is being multiplied by 3. So you'd have to minus out here, you'd have to write minus 16 times 3. Amy, you could do that. You see what just happened? I did the plus 16 inside, and I did minus 16 times 3 outside. Are you allowed to do that, Amy? Yes. If you wanted to, you just have to balance everything out appropriately. Going. Oh, great. Section 10.8. I was looking forward to this all week. I could barely contain myself over Thanksgiving. I just kept saying, forget this food. I want to get back to Gateway and do section 10.8. I figured. Yeah. All right. So what does it say? It says use the given graph of the quadratic to find the solution set of the inequation or inequality. So I'm confused. Oh, okay. Well, this is an equation, and this one is an inequality. So when we say, when is the parabola equal to 0, what are we asking for? This is a pretty good conceptual question right here. When we say, when is the parabola equal to 0, what are we really asking? Yeah, we definitely are looking for the x-intercepts. When you set an equation equal to 0, you're asking for the x-intercepts. Why is that? Is that just something we memorized, or does that make sense that they're asking for the x-intercepts?
Because x is 0.
X isn't 0.
Oh.
When you plug in, right, so let's think about it. Here, you can go ahead and put a little dot. Our x-intercepts are -3 and -1, right? So what happens if I plug -3 into that formula? That'd be -3 squared plus 4 times -3 plus 3. That's 9 minus 12 plus 3, which is -3 plus 3, which is 0. So sure enough, that's 0. But why? What is that really saying? You know what's missing from the front of this equation if I could erase my 37? What goes out front? It's a formula, right? It's y equals x squared plus 4x plus 3. Are we really talking about a function? I suppose that could be f of x equals that formula, or y equals that formula. What are we really asking to be 0? Are we asking for x to be 0? What we're really saying is when is y 0? That's what this formula is saying. When we set a formula equal to 0, we're saying that we want the y value of the coordinate to be 0. And what is the y value of an x-intercept? Like this x-intercept is -3, 0, and this x-intercept is -1, 0. When is the y coordinate equal to 0? only when it's on the x-intercept, right? Because you can tell both of those y values are 0. Furthermore, the y itself, y is the y-axis, right? And the y-axis represents height. You know, you could either be up here with a positive height, or you can be down here with a negative height, or you can be right here where your height is equal to 0. This x-axis here represents a height of 0. Right? Does that make sense that the x-axis has a height of nothing? You're not high up, you're not low down, you're exactly equal to 0. So when we say, when is the function equal to 0, we're really saying, when is the y-coordinate equal to 0? When is the height nothing? And that's why we're talking about x-intercepts. Because if your height is nothing, you're on the x-axis, which means you are an x-intercept. Okay, so that's why the solution is -3 and -1. I realize we could have just looked at that and said, when is the function equal to 0, when x equals -3 and -1, because you're looking for the x-intercepts. But I hope that all that makes sense as a package, why that's true. So given everything we just said, when is x squared plus 4x plus 3 greater than or equal to 0? What does that mean? What does this represent again? It represents the y value, which is really your height of the graph. So when is the height of the parabola? When is it, at what point on the parabola are you either above the x-axis or on the x-axis? Right? There's two questions here. It's greater than or equal to. So let's do both of those. When are you on the x-axis? At -3 and -1, right? So you're on the x-axis. The height is equal to 0 when x is equal to -3 or -1. Right? Same answer as before. But when is your height above 0? Meaning, when is the parabola above the y-axis? Take your pencil and shade it in. Here is where the parabola is above the x-axis, and here is where the parabola is above the x-axis. Oops. You all agree? It's kind of funny. I'm chopping off this little bottom part of the parabola. I'm saying the bottom part of the parabola is no interest to me right now, because I was only asking, when is the parabola on the x-axis? When is the parabola above the x-axis? So when is the parabola above the x-axis? According to the x-axis, the parabola will be above the x-axis when your x value is anything to the left of -3. Right? If you plug in -4, you're up here. If you plug in -5, you're up here. If you plug in -6, you're up here. So we're looking at all the x values to the left of -3, or all the values of x to the right of -1. Any value to the right of -1, you'll also be on the parabola up here. So the answer would be that your height, the parabola, is above the x-axis when either x is less than -3 or when x is greater than -1. Another way we could say all this is, what values of x can I plug into this function such that it'll be positive? What values of x can I plug into that function so that the whole function will be positive? And you know, again, you just look at the whole x-axis and consider it point by point. If I plug -4 into the function, what will it equal? +3, so it'll be positive. If I plug -5 into the function, what will it equal? I don't know, some big number, maybe 10. If I plug in -6 into the function, what will it equal? Again, some big number, still positive. So I can definitely plug in any value over here, and if I plug any of these values into that function, the value will be a positive number, so it will make this statement true. Or if I choose any number to the right of -1, like say I plug in 0. If I plug 0 into the function, that's 0 plus 0 plus 3, that'll be positive, specifically right there. And so that'll also make the function positive. Okay, well, so how do we write down our final answer? Which x values will make this parabola positive? Any of these values here, from -3 to the left, and any of the values from -1 to the right. And we write this in interval form. I forget. Have we already talked about writing down domain and range?
Sort of.
In interval form?
So it's like x such that x is.
So the domain then would be, oh, right, we did do a little bit of domain. Well, you just tell me if this looks familiar. The domain would be from -infinity to 3 or from -1 to +infinity. Have we done that?
Yeah, we didn't try it that way though. We did the other way.
We did it with what? Oh, she did it a little bit with you, Megan? Well, the other way you could say it is, that was a while ago. You could also just say when x is less than or equal to -3, right? Any of these values over here, or x is greater than or equal to -1. Both of those answers would be correct. We're just trying to give a complete summary and report of which x values can I plug into this function so that this function will either be equal to 0 or more than 0. And I think for our case, because I don't think we've practiced interval form very much, that would be our answer. Now notice this is a very visual thing. We're just looking at the parabola. We're saying when is the parabola above the x-axis? Here and here. And therefore the x values I can plug in are here and here. It's almost like we're looking at the shadow of the parabola. It's like we put a light source up here and we shine the light down and we're looking at where the parabola casts a shadow on the x-axis. Someone just raised their hand. Was it you, Alex? Is that Karina?
When you write that, wouldn't it just be easier to make
Say it again? No, let me. You can't say that. That's different. You're literally, now, if you don't mind, I'm going to share that with everyone. You're writing, how did you write this? Like that? You're saying, yeah, no, you can't do that. Because you're saying that x is less than -3, right? What's a number that's less than -3?
Oh, that's actually.
This is actually a pretty funny paradox. What's a number less than -3? Maybe -5? Okay. Well, what's a number greater than -1? -1. Can x simultaneously be smaller than -3 and yet greater than -1? No, so actually this is pretty funny, Karina. Well done. I've never seen anything like that. It's a paradox. It's a paradox. X can't be smaller than -3 and greater than -1. You have. And Karina, thank you for bringing that up. Folks, what if I had asked the opposite question? What if I said, when is x squared plus 4x plus 3 less than 0? All right, let's just change the problem real quick. When is the parabola under the x-axis? This is a great question to ask. Everybody, let's do it. When is the parabola under the x-axis? Well, if you just highlight it, that's it. This is the only portion of the parabola that's less than 0. And so what x values are we talking about? We're talking about the x values between -3 and -1. And if that were the case, so everyone write this down with me. You should have a little bit of space. Well, good, there's 3 such problems for us to do. Come over here to the right. If you were to do x squared plus 4x plus 3 is less than or equal to 0, when is the parabola less than 0? When your x value is between -3 and -1. And if that's the case, Karina, we'd write the numbers down in order from left to right, just like we read. When x is greater than -3, but less than -1. That's what you would say. So folks, that's the answer to the alternate problem. When is the parabola less than 0? That is, when is it below the x-axis? Anytime the x values are between -3 and -1. That's a really good problem for us to do. I think the next problem does that. But now, does that make sense? Yeah. Now you notice, Karina, what was the only difference between your answer and the answer we just wrote down? What was the difference? Yeah, the signs are flipped. This is real. This is a paradox. But it's a delightful paradox. I like it a lot. If I could get a tattoo, maybe that would be it. I would replace X with JW. Yeah, that would be a hoot. Okay, thank you, Karina. Great questions. Now, which one did we just do? Oh, yeah, we already did number 1. We just did number 2. So now let's go down and look at the third one. What one? Oh, yeah, at the math.
Yeah, nobody else would get it.
Yeah. Okay, so hopefully, folks, I think we're all prepared to do this problem now. It's saying, where is the parabola less than or equal to 0? That means when is the parabola below the x-axis? So take your pencil and shade that part of the parabola in. Right? They're asking for that part of the parabola. When is the parabola less than or equal to 0? And notice, what is the y value of the parabola down here? Negative numbers. Yeah, when does the parabola take on negative values? What value, they're really saying, for what values of x will the parabola take on negative values? So for what values of x will the parabola take on negative values? X has to be anywhere between 4 and 7. So real quickly, the answer is x is less than or equal to 7 and greater than or equal to 4. And that would be the answer. And Karina, that's using the notation you were thinking about. You'd say whenever x is between 4 and 7, so in other words, if I take any number between 4 and 7 and plug it into that formula, guess what it's going to equal? A negative number. And so let's just try one. What's a number between 4 and 7? Choose anything. 5. If I do 5 squared minus 11 times 5 plus 28, that's 25 minus 55 plus 28. That's negative 30 plus 28, which is negative 2. So sure enough, I chose any number between 4 and 7, I calculated it, and it was negative. And that's what they're asking. For which values of x can I plug in such that this function will compute to be negative or a 0? What value of x do I have to plug in to make that function equal 0? When will that parabola actually equal 0? Remember, we're asking about the height of the parabola. When is the height of the parabola exactly equal to 0?
0.
Well, that's true. The height would be 0, but what x values will the height be 0? Yeah, 4 and 7. So what if I plug in 4? That would be 4 squared minus 11 times 4 plus 28. And that's 16 minus 44 plus 28, which is negative 28 plus 28, which is 0. So 4 and 7 are when the parabola is actually equal to 0. Anything between 4 and 7 is when the parabola is negative. Folks, just to break this down into two separate questions, if the question was, when is x squared minus 11x plus 28 equal to 0, the answer would be x equals 4 and 7. Is that fair? If the question was, when is x squared minus 11x plus 28 less than 0, okay, strictly less than 0, what would the answer be? Anything between 4 and 7. So you notice I took away the less than or equal to symbol. I'm just saying strictly. If I'm strictly between 4 and 7, my parabola will be negative. But if I make x 4 or 7, it'll be 0. But if I choose anything between 4 and 7, including 4 and 7, my parabola will be either less than the x-axis or on the x-axis. How does that all feel? This is a visual look. This is a visual look. So of course, if we wanted to make this a little more challenging, what would we do? Take away the graph. And then you would no longer be able to look at the graph, and you'd have to be able to answer the same question just by looking at the formula. And in fact, isn't that the next problem? Kind of, yeah. So now we're going to look at the same questions, but we'll look at without a graph. So can we go ahead and do that? Now, just because they don't give you a graph doesn't mean you can't just make a graph, right? You can always just make a graph. So let's look at that first function, number 70. It says, when is x minus 6 times x plus 5 greater than 0? Folks, just for fun, let's make a graph. Okay. What would that graph look like if it was y equals x minus 6, x plus 5? What do these two binomials represent? They represent x-intercepts. Where's this x-intercept? At plus 6, 1, 2, 3, 4, 5, 6. There's one x-intercept. What does this one represent? Negative 5, 1, 2, 3, 4, 5. And where's my parabola? Can you see it in your mind's eye? There. So even though they didn't give me a graph, I just went ahead and drew one. Any questions on how I produced that parabola? Is my parabola perfect? No. But do I have the right x-intercepts? And can I clearly tell when the parabola is below the x-axis versus when it's above the x-axis? Yeah, I can clearly tell based on just this quick sketch. So notice now what they're asking. They're saying, when is this parabola greater than 0? Meaning, when is it above the x-axis? So I'll go ahead and shade that in. This part is above the x-axis, and this part is above the x-axis. So for which values of x can I plug into this function to create this tail of the parabola or to create this tail of the parabola? Yeah, exactly. So this is -5 and this is 6. Anything past 6 this way, so any value of x greater than or equal to 6 will produce that tail of the parabola. And anything past -5 this way will produce that tail of the parabola. And so on my number line, I would say, I would come here to 6 and shade in anything that way. And I'd come over here to -5. Oh, you're right, thank you. It'd have to be what? Yeah, you mean an open circle?
Yeah, my bad. Oh, yeah.
Yeah. There we go.
It was something like that.
Yeah, no, you totally got it. You are correct. So that's what the number line would look like.
Oh, and you can write that as your answer?
And you could write down as your answer, you could say, when x is less than -5 or x is greater than 6. So you could do it both ways. You could write your answer as a number line, or you could write your answer as, in words, when x is less than -5 or x is greater than 6.
Which could also be written with the other way, so that they're similar.
You would not be able to write, when it's shading in opposite directions, you can't put x in the middle.
Oh, okay.
That's what causes the paradox. You can't put x in the middle if it's shading in 2 different directions. Yeah. Technically speaking, when x is in the middle, that means that you've shaded something like this.
Okay.
Shading in the middle. Because x is literally in the middle. So that's what that looks like. This notation is only when you shade between two numbers. Layla.
So I was wondering, why are the signs not?
That's a very good question. Remember when we were asking about this before, when is this equal to 0? We use the zero product rule, which states that this times this equals 0. And if something times something equals 0, what do you know about one of those?
One of them has to be.
One of them has to be 0. So that means that either x minus 6 is equal to 0 or x plus 5 is equal to 0. And so literally you ask, why are the signs opposite? Because now to solve for the x value that will make this thing 0, I add the 6 to the other side, which changes the sign and it becomes 6. So that's why it's positive. That's why the x minus 6 actually is positive 6. Okay. Well, folks, that's it for number 70. They were asking, when is that parabola positive? That is, what is responsible for establishing those two tails of the parabola? And it's any x value that you plug in to make that so. Do you want to check one? Choose. Yeah, you do. Choose any value over here. Any easy value.
You're not supposed to ask questions that you don't want to know the answer to.
Yeah, I know. Karina, go ahead. You get to choose any value. 7 is a great value. Let's say we choose 7.
Now
It's very
we're
easy
going
to check. Just look how easy it is to check. 7 minus 6 is 1, and 7 plus 5 is 12, and 1 times 12 is 12, and is that number positive? Yeah, so that worked. What about a number over here? Choose an easy number. -7 again. So -7 minus 6 is -13, and -7 plus 5 is -2. And is negative times a negative positive? Yeah, so that's also correct. So thanks, Karina. That was a good idea to check a value from both sides to really prove to ourselves that any number you choose from those two tails will produce a positive value. Okay, so now how about here? Here's a formula that's not already factored. Can we factor it?
We can't.
You can?
9 divided by 2.
Is there a number that multiplies to make 18? That adds to 9? Maybe. We're multiplying to make a positive 18, so it's either plus times plus or minus times minus. But we want to add to negative 9, so what is it? Negative 3, negative 6? So we rewrite our question as p minus 3 times p minus 6. When is that greater than 0? Now, because it's factored, we already know where our x-intercepts are. We'll label. Where are my x-intercepts? Not at negative 3, but positive 3 and positive 6. So folks, I want to try something slightly new with you this time. We know that these two values are special. They're like cutoff values. And we know that if I were to draw a picture of this parabola, my x-intercepts would be 3 and 6, which would mean one of two things. Either my parabola looks like this, or my parabola looks like this, right? It's either up, right side up or upside down. But it definitely goes through those 2 points, 3 and 6. Now, of course, you all know which it is. Which is it? Is it right side up or upside down? What is it? It's right side up. How do you know it's right side up? Yeah, because the first term is positive. So we know that it's right side up. So we can already now visualize this whole answer just by thinking about it, that when is the parabola positive? Once again, this tail or this tail. So we now know the answer. When is our parabola, for what values of p can you plug in here that the answer will be positive? Anything left of 3 and anything right of 6. Right, so we can shade that in, anything over here or anything over here. Yes, it would still be an open circle. Thank you. Absolutely. Whenever you use like x is less than or x is greater than, it's an open circle. And whenever you do x is less than or equal to or greater than or equal to, it's a closed circle. So it's strictly whether or not it's strict less than or greater than, or less than or equal to, greater than or equal to. Shading literally means equal to. That's what shading means, equal to. And so since there's a line underneath meaning equal to, you'd shade it in. And here there's no equal to, so you don't shade it in. What does shading mean? Yeah, literally. All right, well, so at this point, folks, we would say, when is the parabola positive? When p is less than 3 or p is greater than 6. You've noticed that the key to doing this process is being able to factor, because that way you see the x-intercepts and you can visualize the parabola, and you can just see when it's positive above the x-axis or negative below the x-axis. Oh, you're on that. All right, well, that's 2 examples of greater than. I'm hoping if we turn the page, it's going to have some examples of less than.
Yes.
Oh, good. Yeah, sure enough. Thank you, folks, for your questions. I guess we're done with that. Now, folks, it's because of our excellent knowledge of parabolas and how to graph them, and the fact that when you factor it, you find the x-intercepts, that we can do this process so simply. The book offers a different approach, and so I'd like to share that approach with you. So let's go ahead and begin the usual way. We have some quadratic, which represents a parabola, and we want to know when is the parabola negative. Conceptually, what are we asking? When is the parabola what?
Less than 0.
Yeah, below the x-axis. That's what this question is asking. They're saying, hey, there's some parabola, when is it less than 0? Which means when is the parabola negative? So we have to take that standard form equation and do what to it? Factor it. So we'll go ahead and factor it. What multiplies to make 10? It adds to make 3? Yeah, so s minus 5, s plus 2. Now that tells us our critical values. So we can take the opposite of those critical values, go and put it on the number line. So what do we got? -2 and +5. Layla, why did I use an open circle?
Well, it's, less than.
Yeah, because it's less than. It's not less than or equal to. If it was less than or equal to, I would have used a solid circle. But since it's just less than, I'll use an open circle. Yeah. All right, so now the question is, do we shade in the middle or do we shade outside? Now, you all can go ahead and just look at this and tell me, should I shade in the middle or on the outside? We're going to shade in the middle. So we already know the answer. We know we just shade right in here. Right, that is the answer. We're already done. Because we're visualizing what a parabola looks like and what it means for a parabola to be below the x-axis. Okay, so now I want to show you the technique the book shows, and I want to show it to you because it's a technique we use in calculus. In fact, my calculus class was using this technique just a couple weeks ago. So I want to share it with you. And it's called try a test value, okay? So everybody just make a little star. Try test values. Okay, so I'm going to erase my shading. And here's what I'm going to do. I want to know when my parabola is less than 0. Well, what I know already is that it's equal to 0 at this point and this point. And what I don't know is over here is either positive or negative values. Here is either positive or negative values, and here's either positive or negative values. But I don't know what yet. So let's choose a test value from each interval. So choose an easy value from over here. Jeff, choose an easy value from over here.
-4.
Okay, great. That's a nice. So I'm going to write down try -4. And Claudia, choose an easy value from in here. 2. So I'm going to try 2. And then choose an easy value from over here as in 8. So over here we're going to try 8. Everybody write that down. We used factoring to find our critical values when the function is actually equal to 0. And now that broke it into 3 intervals. I've got an interval to the left, an interval in the middle, and an interval to the right. And I'm just going to try a test value from each of those intervals to see if the function is positive or negative. So what if I'm going to come down here. What if I try -4? Well, that's going to be -4 squared minus 3 times -4 minus 10. That's 16 plus 12 minus 10, which is 28 minus 10, which is 18, which is positive. Does that surprise us that my parabola is positive to the left? No, because we already knew that. We already knew the parabola was positive over here to the left. Now keep in mind, it doesn't matter that I tried the value -4 and it gave me positive 18. What matters is that the number was positive. It doesn't matter that the number was 18. It matters that it was positive, because that tells me that over here in this interval to the left, my parabola is on the positive side. So the numbers don't really matter. It's the fact that it's positive. Okay, what about try our number from the middle? Try 2. If I try 2, that'll be 2 squared minus 3, 2 minus 10. That's 4 minus 6 minus 10, which is -2 minus 10, which is -12. The 12 doesn't matter, but the fact that it's negative matters. That means that any value that I choose in that middle interval is going to be negative, which means what about my parabola?
Yes.
It's down below. And then if I try a number from that far right-hand interval, I try 8, and that would be 8 squared minus 3 times 8 minus 10. That's 64 minus 24 minus 10, which is 40 minus 10, which is 30. The number 30 doesn't matter. What matters is that it's positive. That means the value of the parabola is positive off to the right, and we already knew that. The parabola has positive values off to the right. So this is called trying test values. You just try a value in that region, and in that region. And just by noticing that it's positive, negative, positive, that told us, if you didn't already know what the parabola looked like, you could take a look at the parabola, put in the values -2 and 5. And negative means below the x-axis, so you know the parabola looks like this. And then to the right and left-hand side is positive, so it looks like that. What do you think about this method of trying test values? It does seem a little long, and obviously doesn't it tell us something we already know? It kind of does. It's really just confirming what we already know. But in some contexts, you do need to do this. Like I said, in calculus, it's very handy. In calculus, you would have to do this in particular contexts to just try test values to know when the function is negative or positive. All right, folks, we have one more to try. Oh yeah, wow. Okay, we're almost done. So we want to know, when is the parabola less than 0? And again, if you wanted to visualize it, we've got some sort of parabola, and we want to know for what values is it less than 0. Yeah, or equal to. So we're including those values. So what do we do to our function? Factor it. What multiplies to make 18 that adds to make 3? Yeah, 6 and 3, which ones?
-6.
Yeah, t minus 6 and t plus 3. Very good. So, and we want to know, when is that less than or equal to 0? Well, we already know our critical values at positive 6 and at negative 3. And Layla, am I using an open circle or a closed circle? Exactly right. Because shading means equal to, exactly right. All right, so, well, when is the parabola negative? In between those two values. And in fact, you could do a test value. And in fact, there's a very easy test value to try, isn't there? 0. If I plug in 0, 0 squared minus 3 times 0 is negative 18. And sure enough, it's negative. So any value in here is going to produce a negative value for the parabola, which we already knew, as we can look. So our answer is when t is less than or equal to 6, but greater than or equal to negative 3. That would be the answer. Any value at all. This is really kind of powerful, folks. Any value between negative 3 and 6, if I plug it into this formula, the answer is going to be negative.
So where are the word problems that we have to do?
They're on the next page. Good question, Maria. If we have time, maybe we can go back and do the completing the square when the first term was negative. Did I already give you guys your practice test?
Nope.
Okay.
No,
Nope.
I didn't?
no, you didn't.
No, I needed to hand back up.
That's why I asked.
Because I was joking around and said I didn't.
Ah, here it is. Oh, cool. Well, at least I brought it. Oh my. Yeah, and I will pass back quizzes as well. All right. Okay, ready, folks?
Horrible, horrible children.
Let's do it. The profit made when T units are sold. Okay, so you're just some company and you're selling units of something. What should we be selling? We could be selling cars.
Are you thirsty?
We could be selling anything. So the profit made when T units are sold is given by that formula. So everyone go ahead and write down the formula. This is your profit formula. So the first thing we'd like to ask is, what does that parabola even look like? After all, if we can go ahead and just look at a graph, and Maria, I'm so glad you asked that earlier. You're like, why would you even want to look at a graph? This is one time you'd want to look at a graph to see really quickly, what are my profits going to be? So can we factor this? What multiplies to make 154 that adds to make 25? No clue. 154 is divisible by 2 is 76. Now notice, when you're trying to factor 154, once you factor it once, you can just look at the number 76. What goes into 76? Does 3? No. 2 does. So that means if 2 goes into 76, then 4 will go into it. So 4 times half of 76 is 38. So I tried 1, 2, 3, 4, 5. 5 doesn't go into it. 6? No. Why doesn't 6 go into it? Because 3 didn't go into it. If 3 didn't go into it, 6 can't possibly go into it. Okay, 7? No, 7 doesn't go into 38. 8? No. 9? No. 10?
'Cause you divide by-
Oh, you're right. 8 would go into it. Yeah, 8 doesn't go into 38, but 8 goes into that. So, okay, so 8 times 19. But let's see, 19 is prime. So now we know that I don't think any more numbers will go into it. Let's see, 9, 10.
Wait, no.
No, 11 should. What's happening? No, 14.
8 plus 19 is 25.
Oh, yeah, it is. I feel like I just skipped some factors of 154.
No, it's 27. No,
What's 27?
8 plus 19.
Oh, I think I messed up. Just 3. 3 doesn't go into it.
14.
Yeah, 11 and 14. But if 11 and 14, that means 7 has to go into it. And I skipped 7. 7 goes into 15.
7 didn't.
21 times. No. 7 and 22. Okay, there we go.
It's okay, you can't do it.
Yeah, I was going a little too fast there. 11 and 14, thank you. Oh my goodness. All right, is that our factor table? That's our factor table. Okay, and which one of those will actually add to make 25? 11 and 14. So now we can go ahead and factor. This is really t minus 11 and t minus 14, which tells us the critical values are at 11 and 14. And so we can already imagine that here's our profit. There's our profit curve. Okay, so this graph represents the profit our company is making. And obviously, you hope your profit is positive or negative? Positive. We all want to make money. So that means to positive profit, we can either make less than 11, or we can make more than 14. Right? Does that immediately make sense? If you want to have a positive profit, the number of units that you sell has to be less than 11 units or more than 14 units.
It's really strange.
It is very strange.
Really strange.
Yeah. Perhaps this model is only supposed to be considered for units more than 14.
It would have to be.
Yeah.
How would you not
Should be
make
like-
a profit?
Yeah, it doesn't make a lot of sense. So determine the number of units to be sold in order for the profit to be negative. So to take a loss, that means you'd have to be selling between 11 and 14 units, right? Because if you sell 11 units, what was your profit?
Supposedly like plus $1 or something.
No, if you literally sold 11 units, your profit
Zero.
was 0. And if you sold 14 units, your profit was 0. But if you sell between 11 and 14 units, your profit is going to be negative. Now, can you sell any number of units between 11 and 14?
Wow.
Can you sell 11 and a half units? I mean, if you're selling a car, that would be challenging. You can't sell 11 and a half cars. But maybe if you're selling something like gallons of water at a water shop, and people can take as many gallons as they like, then sure, maybe that would be possible. But if we're only considering, okay, so let's see. T, strictly speaking, has to be between 11 and 14. Right, the number of units, if you're between 11 and 14, that means you're taking the loss. And this assumes that you can sell a fractional number of units. But what if it's only a whole number of units? What if it's cars? Specifically, how many cars will generate a loss? 12 and 13, and that's it. So this model suggests that if you sell 12 or 13 cars, you're going to have a negative profit. If you sell 11 or 14 cars, you make no profit. And for some reason, if you sell less than 11 cars, you have a profit, and if you sell more than 14 cars, you have a profit.
Just me.
Yeah, I don't understand this part of the curve either. I don't understand. It's just, yeah, I don't know why if you only sell a few things, you'd make a profit. But as you sell more, it cuts into your profit. But then if you make more than 14, it could be, yeah. Not sure.
Yeah, that's-
You know, ultimately, it's probably just not the best form of word problem. But the mathematics, we totally understand. We want to know when the parabola is less than 0, so that's it, between 11 and 14. All right, that was number 74. Let's take a look at 75. A coin is tossed upward from a balcony, 166 feet high. Have any of you ever done that? Stood on the balcony of a building and thrown coins off? Yeah, well, we looked at, did anyone look up the terminal velocity of a coin off a building? It's only like 50 miles an hour.
Yeah.
I mean, you could throw a coin at someone's head at 50 miles an hour. Baseball players throw balls at 100 miles per hour. So I could throw a coin at Jordan's head at 50 miles an hour. No, not me. I would be a lob or an under, yeah. Okay, so
Why did you answer? What did I do?
I just chose you because I thought it'd be funny. I couldn't throw it at a girl, Jordan. That'd be rude. Yeah, you understand. All right, so a coin is tossed upward from a balcony. Again, this is a time where drawing a graph is nice. So imagine here's your x and y axis, and here's a building, right? This is our building. And so we're going to throw the coin up and down, right? The coin is tossed upward from a balcony, 166 feet high. So that's 166. With an initial velocity of 16 feet per second. I don't know if that's important yet, that it's going 16 feet per second. And during what interval of time will the coin be at a height of at least 70 feet? This is a really good question. They're saying, over what interval of time, and we know that this is our time axis, so we're saying from time equals 0, the moment you throw the coin, for how many seconds will the coin be at least 70 feet high?
It's gonna be like 0 to something.
Yeah, exactly. It'll be from 0 to something. Because if this is 166, we're 70 feet. Maybe around there. That looks roughly it. And so if we follow 70 feet over to the parabola to here, we're saying the coin is at least 70 feet high all along from here to here. And in fact, I'll trace it. Is that fair? That the purple arc represents all the time during which the coin is at least 70 feet high. How helpful is this drawing? I think it's pretty helpful because it really gives you a visual understanding of what we're even talking about. So, again, a coin is tossed upward from a balcony 166 feet high with an initial velocity of 60 feet per second. During what interval of time will the coin be at a height of at least 70 feet? So, the interval of time goes from 0 all the way to question mark. I don't know when that time is, but we apparently want to solve for that question mark. And they're telling us that your height function, this is the height function, telling you how high it is negative 16t squared plus v naught t, where v naught t is what? V naught t is probably the initial velocity, and h naught is your initial height. So let's write down our formula. Our formula is that the height is negative 16t squared. And what was our initial velocity? 16t. And what was our initial height? 166. Now this is the critical moment. How do you take an equation and make it ask a question?
Because it needs to be equal to 70, right?
Does it need to be equal to 70?
Greater than it.
Yeah, greater than or equal to 70. So how do I say that I want this thing to be greater than or equal to 70? I just put a little greater than or equal to 70 at the end. I know that might seem like a small thing, but that's the critical skill that we're looking at here, is how do you take an equation and ask a question? We just asked this an equation a question. We said, hey, when are you, the height, greater than or equal to 70? So now we go about doing it. What is it we need to do again? We need to do what to our equation? Factor it. Yeah, we want to factor it. How do we factor something? We need everything to be on the left-hand side. We need to group all of our terms. So what are we going to do with our 70? Yeah, let's go ahead and bring it over. And so now what we're really asking is, when is negative 16t squared plus 16t plus 100, no, plus 90, no, plus 96? Greater than or equal to 0. Is that it?
Yeah.
166 minus 70 is 96? Yeah, I guess it is. All right, so that's our question. When is that parabola greater than or equal to 0? What can we do to this quadratic to make it easier? Hopefully factor out the negative 16, which would leave behind with what?
T squared plus 1t.
Plus 1t? We're factoring out a negative. What does that do to all the signs? Yeah, they change all the signs, so t squared minus 1t. And then is 96 divisible by 16? 6. Is it positive or negative 6? Negative 6. So remember, when you factor a negative out, when you factor out a leading negative, all the signs change. So instead of being minus plus plus, it becomes plus minus minus. And what can we do with that friendly little negative 16?
Divide it off.
We could divide it off. Now, if we divide it off, what happens when you divide by a negative? You technically have to switch the sign, or switch the symbol, right? Because this is currently greater than or equal to. So if we do that, we would have to switch it to less than or equal to if we divide off the negative 16. Do we even have to divide off the negative 16? Okay. Let's do it. Because that's what we want to do, right? Is get rid of the negative 16. So we're going to divide that off. And 0 divided by negative 16 is just 0. So now it's going to be t squared minus 1t minus which is less than or equal to 0. So when is that less than or equal to 0? Notice that this kind of changed the problem a little bit. First, we were wondering, when is this quadratic above the x-axis? But now we're asking, when is this quadratic below the x-axis? This is interesting. This question right here was saying, I have a downward sloping parabola, and I want to know, when is it positive? So we were looking for that, a region in between. And now we transformed it into this graph, which is an upward facing parabola, and we're asking, when is it below the axis? Which, again, you're saying you're looking for a region in between. So even though it transformed the question, the answer to both is still going to be the same.
And also, it's not really talking about 0 though. If 0 was adjusted up to 70.
Right.
Yeah.
So what's our factoring?
3.
What is it?
2.
Yeah, 2 and 3, so it's t minus 3 and t plus 2?
Yeah.
And so what is that? And we're saying, when is it less than or equal to 0? Well, first of all, what's our critical t values?
3 and
3 and negative 2. Now that's weird. Time is negative 2. What does time negative 2 mean over here on our original?
that if you could go lower until
Yeah, if the parabola continued this way, where would it hit? At negative 2. And since the parabola does go this way, where does it hit? Well, actually, we don't know about, hold on. We just solved the actual question, which is, when is it above 70? Oh, there it is, above 70 feet. See, over here, the parabola was still above 70 feet to the left. So that was the value of it being above 70 feet. So that would be, right there is our negative 2 value. And right here is our positive 3 value. There we go. Do you see how the parabola technically does continue to the left and is still above 70 feet? And over here, the parabola is above 70 feet. That's where the negative 2 and the negative 3 are. Now, can we have negative time? No. So what are the actual time values that we're looking at? Between 0 and 3. So anywhere between 0 and 3, the coin was at least 70 feet above the ground. All right, well, that worked out, folks. So, negative 2, is that an extraneous answer?
Yes.
Negative 2 is an extraneous solution.
But not really, because if it didn't have a negative 2, how would we know that you have to include 0?
Yeah, exactly. So what we're really saying is that between negative 2 and 3 is the overall region where the height is at least 70 feet. And we had to then know to cut down the region from negative 2 to 3 to cut that down from 0 to 3 because we're only talking about positive time. So ultimately, what's the answer? During what interval of time is the coin at least 70 feet? Between 0 and 3 seconds. So if you just looked at the answer t equals negative 2 and 3, you wouldn't necessarily have known to cut that down to 0 to 3, except for the fact that you drew a really nice graph to start with, and you knew that time had to be positive. That's a nice application problem. All right. First, here's your practice test. There's 2 for you. 2. Why does it feel so long? Oh, well, I did have the answer key on the back. Oh, actually, it's only 4 pages. Okay, that's not as long. Oh my God.
And then this is due.
How do you do that? Oh, it is. Oh, I did. Oh, thank you. For reminding me. I did send it out in the email. Okay. What? I think it's due on Thursday.
This Thursday?
Yeah. No, folks, can we talk real quick? So